Welcome. In this video, we will explore the fundamental concept of integral calculus, finding the area under a curve. This is a core topic in the IB Mathematics Analysis and Approaches higher-level curriculum. By the end of this session, you will be able to approximate the area under a curve using rectangles, understand the formal definition of the Riemann integral, and use graphical methods to evaluate simple, definite integrals. Let's begin with a classic problem, one that Archimedes tackled over 2 millennia ago. Our goal is to find the exact area, which we'll call A, enclosed by the curve y equals x squared, the x-axis, and the vertical line x equals 1. This is the area under the parabola from x equals 0 to x equals 1. Here's a graph of the function y equals x squared. The area we are interested in is the shaded region between the curve and the x-axis, from the origin to x equals 1. Since the shape is not a simple rectangle or triangle, we need a method to find its area. We'll start by approximating it. Let's start with a very rough approximation. We can use a single rectangle to get a lower bound for the area. Consider this blue rectangle. Its base is the interval from 0 to 1, so its width is 1. Its height is the value of the function at the left endpoint, x equals 0, which is f of 0 equals 0. This rectangle has 0 area. This is clearly an underestimate. Let's try a different rectangle. What if we use the height at the right endpoint x equals 1? This rectangle has a width of 1 and a height of f of 1, which is 1 squared, or 1. Its area is 1 times 1, which is 1. This is clearly an overestimate, as it includes a large area above the curve. So we know the area A is somewhere between 0 and 1. That's not very precise. Let's refine our method. A better approach is to divide the interval into several smaller subintervals and use rectangles on each. Let's divide the interval from 0 to 1 into 4 equal strips. Each strip will have a width of 1/4. We can now draw rectangles on each of these subintervals. Let's start with lower rectangles, also known as a lower Riemann sum. For each subinterval, the height of the rectangle is determined by the lowest value of the function in that interval. Since y equals x squared is an increasing function, the lowest value occurs at the left endpoint. The total area of these lower rectangles, which we'll call A sub L, will be an underestimate of the true area A. The area A sub L is the sum of the areas of the 4 rectangles. The width of each is 1/4. The heights are f of 0, f of 1/4, f of 1/2, and f of 3/4. Substituting the function f of x equals x squared, we get 1/4 times 0 squared, plus 1/4 times 1/4 squared, and so on. This simplifies to 1/4 times the sum of 0, 1/16, 1/4, and 9/16. The total is 1/4 times 14/16, which is 732, or 0.21875. So we know A is greater than 0.21875. Now let's find an upper bound for the area using upper rectangles. For upper rectangles, the height of each rectangle is determined by the highest value of the function in that subinterval. For our increasing function, this occurs at the right endpoint. The total area of these upper rectangles, A sub u, will be an overestimate of the true area A. The area A sub u is the sum of the areas of these 4 rectangles. The width is still 1/4. The heights are now f of 1/4, f of 1/2, f of 3/4, and f of 1. Substituting the function, we get 1/4 times 1/4 squared, plus 1/4 times 1/2 squared, and so on. This simplifies to 1/4 times the sum of 1/16, 1/4, 9/16, and 1. The total is 1/4 times 23/16, which is 23/64, or 0.359375. So we know A is less than 0.35937. By combining our lower and upper bounds, we can say that the true area A is between 0.21875 and 0.359375. This is a much tighter estimate than our initial guess of between 0 and 1. This leads to a crucial question. How can we obtain an even better estimate for A? The answer is to use more rectangles. If we divide the interval into 8 subintervals instead of 4, the width of each rectangle becomes 1/8. The gaps between the rectangles and the curve become smaller, leading to a more accurate approximation. Let's see the results for n equals 8. The lower sum, A sub L, is approximately 0.27344. The upper sum, a sub u, is approximately 0.39844. Notice that the interval containing a has become narrower. The lower bound has increased, and the upper bound has decreased, bringing them closer to the true value. This process of using more and more rectangles is the foundation of integral calculus. Let's formalize this idea. Suppose we divide the interval from a to b into n subintervals of equal width. The width of each subinterval, which we'll call delta x, is given by b minus a, all divided by n. We can label the endpoints of these subintervals as x sub 0, x sub 1, and so on, up to x sub n. Here, x sub 0 is a, and x sub n is b. The lower sum, a sub L, is the sum of the areas of n rectangles. The width of each is delta x. The height of the ith rectangle is the function value at the left endpoint of the ith subinterval, which is f of x sub I minus 1. We can write this using sigma notation as the sum from I equals 1 to n of f of x sub I minus 1 times delta x. Similarly, the upper sum, a sub u, is the sum of the areas of n rectangles where the height of the ith rectangle is the function value at the right endpoint, f of x sub I. In sigma notation, this is the sum from I equals 1 to n of f of x sub I times delta x. For any number of subintervals n, the true area A is always bounded by the lower and upper sums. That is, a sub L is less than or equal to A, which is less than or equal to A sub U. This inequality holds true for any positive integer n. Now, what happens as we make the rectangles infinitely thin? This is where the concept of a limit comes in. As the number of subintervals approaches infinity, the width of each subinterval, delta x, approaches 0. The lower and upper sums get closer and closer to each other, squeezing the true area A between them. This limit, if it exists, is the exact area under the curve. This is the formal definition of the definite integral. We define the definite integral of f of x from a to b as the limit of the Riemann sum as n approaches infinity. The symbol is an elongated s, which stands for sum. The numbers a and b are the lower and upper limits of integration. The dx indicates that we are integrating with respect to the variable x. This is known as the Riemann integral, named after the German mathematician Bernhard Riemann, who formalized this concept using limits. Let's apply this formal definition to our opening problem to find the exact area under y equals x squared from 0 to 1. We want to evaluate the integral from 0 to 1 of x squared dx. We'll use the right endpoint rule for our Riemann sum, which corresponds to the upper sum. First, let's find the width of each subinterval, delta x. It's b minus a over n, which is 1 minus 0 over n, or simply 1 over n. Next, we need to find the x-coordinate of the right endpoint of the ith subinterval, which we'll call x sub I. It's the starting point a plus I times the width delta x. So x sub I is 0 plus I times 1 over n, which is I over n. Now we can write the Riemann sum. It's the sum from I equals 1 to n of f of x sub I times delta x. Substituting our expressions, we get the sum from I equals 1 to n of I over n squared times n over n times 1. Let's simplify this expression. I over n squared is I squared over n squared. Multiplying by 1 over n gives I squared over n cubed. Since the sum is over I, n cubed is a constant, so we can pull it out of the summation. We are left with 1 over n cubed times the sum of I squared from I equals 1 to n. To evaluate this sum, we need a known formula for the sum of the first n squares. The sum of the first n squares is given by the formula n times n plus 1 times 2n plus 1, all divided by 6. This is a standard result you should be familiar with. Substituting this formula into our expression, we get 1 over n cubed times n plus 1 times 2n plus 1 all over 6. We can cancel 1n from the numerator and denominator, leaving us with n plus 1 times 2n plus 1 all over 6n squared. This expression gives us the area of the upper sum for any number of rectangles Cn. To find the exact area, we take the limit as n approaches infinity. The exact area A is the limit of a sub u as n approaches infinity. Let's expand the numerator. n plus 1 times 2n plus 1 is 2n squared plus 3n plus 1. So we have the limit of 2n squared plus 3n plus 1 over 6n squared. To evaluate this limit, we can divide every term in the numerator and denominator by the highest power of n, which is n squared. This gives us the limit of 2 plus 3 over n plus 1 over n squared, all over 6. As n approaches infinity, the terms 3 over n and 1 over n squared both approach 0. So the limit becomes 2 over 6, which simplifies to 1/3. The exact area under the curve y equals x squared from 0 to 1 is 1/3. This confirms the result we saw in the table of approximations. The lower and upper sums were converging to 1/3. This rigorous method using limits gives us the precise answer. While the limit definition is powerful, it's often too complex for practical calculations. Fortunately, for some functions, we can find the area using simple geometry. Let's look at an example. We want to find the integral from 0 to 2 of the function 2x plus 1 dx. This represents the area under the line y equals 2x plus 1 from x equals 0 to x equals 2. Let's sketch the graph. The line y equals 2x plus 1 has a y-intercept of 1. At x equals 2, the y value is 2 times 2 plus 1, which is 5. The area we need to find is the region bounded by the line, the x-axis, and the vertical lines x equals 0 and x equals 2. Notice that this shaded region is a trapezoid. We can calculate its area using the formula for the area of a trapezoid. 1/2 times the sum of the parallel sides times the height. The parallel sides are the vertical lines at x equals 0 and x equals 2. Their lengths are the y values at those points. F of 0 equals 1 and f of 2 equals 5. The height of the trapezoid is the distance between the parallel sides, which is 2. So the area is 1/2 times 1 plus 5 times 2, which equals 6. Therefore, the integral is 6. Let's try another example using a different geometric shape. Consider the integral from 0 to 1 of the square root of 1 minus x squared dx. This looks more complicated, but let's analyze the function. If we let y equal the square root of 1 minus x squared, and then square both sides, we get y squared equals 1 minus x squared. Rearranging this gives x squared plus y squared equals 1. This is the equation of a circle centered at the origin with a radius of 1. Since y is the positive square root, y equals the square root of 1 minus x squared represents the upper half of this unit circle. The integral from 0 to 1 represents the area under this semicircle from x equals 0 to x equals 1. This is exactly 1/4 of the unit circle. The area of a full circle is pi r squared. For a unit circle, the radius r is 1, so the area is pi. The area of 1/4 of this circle is pi divided by 4, so the integral is pi over 4. These examples show that when the function's graph forms a simple geometric shape, we can find the exact value of the definite integral without using limits or complex calculations. Now, let's look at some important properties of definite integrals that are essential for problem solving. First, consider the integral from a to a of f of x dx. This represents the area under the curve from a point to itself. Since there is no width, the area is 0. So the integral from a to a is always 0. Second, let's look at the integral from a to b of f of x dx plus the integral from b to c of f of x dx. This represents the area from a to b plus the area from b to c. The sum of these two areas is simply the total area from a to c. This is known as the additivity property. Let's work through an example to see how these properties are used. Suppose we are given that the integral from 2 to 5 of a positive function f of x is 10, and the integral from 5 to 9 of the same function is 12. We need to find two other integrals. First, let's find the integral from 5 to 5 of f of x dx. Using our first property, the integral from a to a is 0. Here a is 5, so the integral from 5 to 5 is 0. Next, let's find the integral from 2 to 9 of f of x dx. Using our second property, the integral from 2 to 9 can be split into the integral from 2 to 5 plus the integral from 5 to 9. We are given the values for these two integrals. The integral from 2 to 5 is 10, and the integral from 5 to 9 is 12. Adding them together, we get 10 plus 12, which is 22. So the integral from 2 to 9 is 22. These properties are fundamental and will be used extensively as we delve deeper into integral calculus. Let's recap what we've learned. We started with the problem of finding the area under a curve. We saw that we can approximate this area using lower and upper rectangles. As we increase the number of rectangles, our approximations become more accurate. This led us to the formal definition of the definite integral as the limit of these Riemann sums. This limit gives us the exact area. We also learned that for simple geometric shapes, we can evaluate integrals directly using area formulas. Finally, we explored key properties like the zero width and additivity properties. You are now able to approximate the area under a curve, understand the formal definition of the Riemann integral, and use graphical methods to evaluate simple definite integrals. These are the foundational concepts for the rest of our study of integral calculus. To solidify your understanding, here are 5 practice questions in the style of IB assessment. Pause the video, work through them, and then resume to see the fully worked solutions. Question 1 asks you to estimate the area under y equals x cubed from 0 to 1 using 4 subintervals. Question 2 asks you to find the exact area under y equals 3x plus 2 from 0 to 4 using geometry. Question 3 involves using the limit definition for a simple function. Question 4 uses the additivity property. And question 5 asks you to find the exact area of a quarter circle. Take your time to solve these. When you're ready, let's go through the solutions. Let's review the solutions to the practice questions. For question 1, we need to estimate the area under y equals x cubed from 0 to 1 using 4 lower rectangles. The width of each subinterval is 1/4. The heights are f of 0, f of 1/4, f of 1/2, and f of 3/4. Calculating these values and summing them gives an area of $164, or 0.015625. For question 2, the area under the line y equals 3x plus 2 from 0 to 4 forms a trapezoid. The parallel sides have lengths f of 0 equals 2 and f of 4 equals 14. The height is 4. Using the trapezoid area formula, we get 32. For question 3, we use the limit definition for y equals 2x from 0 to 3. Delta x is 3 over n, and x sub I is 3i over n. The Riemann sum simplifies to 18 over n squared times the sum of I. Using the sum of I formula, n times n plus 1 over 2, we get 9 times n plus 1 over n. The limit as n approaches infinity is 9. For question 4, we use the additivity property. The integral from 1 to 5 is the sum of the integral from 1 to 3 and the integral from 3 to 5. Adding the given values, 7 plus 4 gives 11. Finally, for question 5, the function y equals the square root of 9 minus x squared represents the upper half of a circle with radius 3. The integral from 0 to 3 is 1/4 of this circle. The area is 1/4 times pi times 3 squared, which is 9 pi over 4. I hope this video has provided a clear and rigorous introduction to the area under a curve and the Riemann integral. Thank you for watching.